Hi, I'm going to talk to you about Chapter 27, which is on current and resistance. We'll talk about a few different types of ways to quantify current, including electron current and sort of regular old conventional current. Look at current density, and then some properties of materials that make them good conductors, and then finally we'll finish it with Ohm's law, which describes how potential, current, and resistance are all connected. Okay, so far we've looked at stationary charges and electrostatics, and in this chapter we're going to start letting the charges move around. I mean, we did a little bit of kinematic problems of charges moving in electric fields. But just to start with some definitions, we have current, we're measuring in units of amps. So let's just write that out, right? So an amp is a coulomb per second. We've done potential difference already here. That is measured in volts, which is a joule per coulomb. And then power we'll actually deal with next time, so we'll kind of skip that. And then resistance we'll look at today. This is, okay, put a sticker here. Fun. Resistance is our main topic of today, and so that is measured in units of ohms. Right, so that symbol, omega, it's a Greek letter omega, OHM is the ohm. Okay, so off we go. Oh, that was my dog. Okay, so okay, sorry. So I had a question on the quiz to see if anybody. You hear that? That's Callie. Okay, so charges move in a circuit if there's an electric field or potential difference that will drive them to move that way. And one of our common sources of potential difference is battery. And so on the left is just a picture here of what inside a typical battery might look like. So you have sulfuric acid, some type of acid in here that causes the reaction between these two metals. So we have, for example, a carbon electrode and a zinc electrode. So the carbon is going to give off electrons, and they'll go over to this side and make the zinc electrode negative. And then, of course, this is what it looks like in just regular batteries that we're used to seeing. Okay. All right. So if we look at what's actually happening, we want to start thinking about current as, this in circuits. It really just builds on what we've done so far in terms of electric fields. And so, current is just charges moving. And so if we look at what's happening inside the wire, right, there must be some electric field that's driving that. So first, let's just look at a sort of a first definition of current, which is electron current here. Okay, the symbol is I sub E, and it's just by definition, number of electrons moving through one point in the wire per second. And so we're always going to be talking about sort of these cross-sectional areas in the wire, right? So if we think about, a slice in the wire, or, it's even shown down here as well, right? So how many electrons are going through that particular surface in the wire per second? Okay, and so that is equal to this relationship. So we have the number density of electrons, so that's N sub E, and it's the number of electrons per volume, right? So Ne is the number of electrons per volume. And this is just a property of the material that we're talking about. A is the cross-sectional area. So if I'm doing just a face-on view of the wire, right, that has some radius r, my area, it's just the cross-section will be pi r squared, the area of a circle. And then drift velocity is a measure of how quickly these electrons are moving, kind of a bulk motion of them all going to the left. So if we look at our units here, right, so we just have the number per volume, that's the number density. We have an area, which is kind of a meter squared, and volume would be like a meters cubed. Okay, and then we have a velocity, which is a meter per second. So on the top, we have a meter times a meter squared. That cancels with our volume of meter cubed. And so we're just left with number per second, right? So it's the number of electrons passing through some vertical part of the wire per second. Or this way if they're going this way. Okay. So let's just think a little bit about how the electrons are moving in the wire, right? So we know that these are negative charges and they are moving in this direction, right? That's their speed. And so that if we recall from electric fields are going to show us the direction, the motion of the positive charges. So we expect our electric field to be to the right, which is what it is. Okay, and now we can try and use like a force analysis to understand what's happening in terms of the wire here. So let's just erase that. Okay. Get this guy out of the way. Okay, so we have, we can just use F equals ma. And then solve for acceleration. So that's force over mass. And you remember that when we're talking about a charge moving in the electric field, the force that it feels due to the electric field is Q times the electric field. Okay, and then so that can give us our acceleration. And then we can keep going to just try and describe what the velocity looks like using kinematics. So this is, we're trying to solve for what the drift velocity is of these electrons. And then we're just using our regular kinematic equation, right? So initial velocity is initial velocity plus acceleration times time. Initial velocity is going to be 0 because they're starting from rest. So in reality, these electrons will feel the field, they'll start moving, bump into an atom, and then start moving, bump into another atom. And so they're kind of making slow progress down through the wire. But there's a lot of electrons, so we end up getting a lot of charge moving. Okay, and then we're just plugging in our acceleration that we had already, right? We'll plug that in here. And it gives us that the drift velocity is the charge times the electric field divided by mass, and then times delta T. So if we just bring now our equation for the electron current that we had from the past slide, we plug in our drift velocity, and that gives us a more complete expression for the electron current. Okay, so so it's the number density of electrons, the charge. Tau is the time between collisions. Okay. All right, so it sounds like we got Darth Vader near me, but that's my dog again. Okay, again, A is the cross-sectional area of the wire, M is the mass of the charges that are moving, and E is our electric field. Okay, so current that we deal with more commonly than is just capital I. So that's what we're using more commonly than an electron current. And so this is just a measure of charge per time. So if you recall, we had the units of IE are number of electrons per second. So we just need to multiply this by the charge of an electron, right? That's what E is. Or proton, they have the same charge. And then we would get, just in terms of units, then we would actually get a measure of the flow of charge in terms of coulombs per second, which is what we want, okay? And then, so note in here, kind of buried in the equation, is this A, which is, remember, the cross-sectional area of the wire, right? So if we're looking at it sideways, right, A is kind of this little cutout of the wire, right? Or if we look at it face on, it's, you know, pi r squared, if it's just a circular wire, which usually they are. Okay, so just keep in mind, right, this current I depends on geometry. Okay, so there is another way to measure current that doesn't depend on geometry, and that's called the current density. And so just to look at the definition here, right, so current density is J. So that's our symbol for current density. And its definition is the current that we just talked about, so coulombs per second divided by the area. So we're dividing now by the cross-sectional area of the wire. And so it gives us a measure of current that doesn't depend on the actual geometry of the wire. It's kind of, per cross-sectional area. And so that would just simplify, again, the charge of the electron, the number density of electrons, and the drift speed. Okay, so let's do an example problem. So we want to find out what the average velocity of electrons moving through copper wire is if the current is 0.1 amps. The wire has a diameter of 2 millimeters, and then the density of charge carriers is 8.5 times 10 to the 8. All right, so, or 10 to the 28. So we are given that the current is 0.1 amps. We are given that the diameter is 2 millimeters, so the radius is 0.001 meter. And then the density of the charge carriers is 8.5 times 10 to the 28 atoms per meter cubed. And we want to find the average speed, which is really our drift velocity. Okay, so if we look back just one slide or two, the current is the charge of the carrier times our electron current, right, which is the number of electrons, the area, and the drift velocity. So we want to solve for this. So we can divide both sides by E and A. So we get I over E and E and A. And then we can plug in. And so we have our current is 0.1 amps. We have the charge of the carriers, 1.6 times 10 to the minus 19 coulombs. We have the number density is 8.5 times 10 to the minus, oh no, to the 28, sorry, not minus 28, atoms per cubic meter. And then we also have the cross-sectional area. So this, remember, is going to be pi r squared. Pi times 0.001 meter squared. I'm running out of room here, but we'll stick that in there. Okay, so then we need to just calculate. Okay, so I'm just running out of room a little bit, but I'll just put pi r squared in there. Okay, and then if I plug everything in, I get that my speed is 2.34 times 10 to the minus 6 meters per second. And let's just convince ourselves that we got meters per second here, right? So our units on the top, right? We have an amp, which is a coulomb per second. And then on the bottom, we had a coulomb. We had an atom per 1 over meters cubed. And then we had a meter squared. Okay, so the meter squared leaves one of those. The coulombs go away. So we get a 1 over second divided by a 1 over meter, which is a meter per second. Yay, that's excellent. Our units work out. Okay. So just note that we just found a speed that was like 10 to the minus 6 meters per second for the drift velocity. So that's super slow. And in reality, electrons are really moving individual electrons are moving very slowly through the wire, but you end up having a lot of electrons that are moving, right? And so you can get a decent amount of overall charge moving through the wire, but the actual speed of electrons is quite small. So different materials have different properties, and so some are better conductors than others. All right, so if we have an electric field that we apply to the wire, and we want to know how much current we get out, it depends on the conductivity or the resistivity. Okay, so it's proportional to the conductivity, or 1 over the resistivity, okay? Okay, and then if we actually want to look at a length of wire, and we can calculate from the material that it's made out of, and the length of the wire, we can actually calculate what the resistance would be. And this is a resistance that's going to be in ohms, right? So this is a measure of ohms. Okay, and so if we had a length of wire, it's got a length L, and on the side of it, it's got a cross-sectional area here of A. Okay, so we have that, the length, we have the area, and then we would just use the resistivity, rho, right, from this column, and we could actually calculate then what the resistance would be of a particular wire of a particular length and diameter, right? And again, remember A is going to be pi r squared if we just have a cylindrical wire, which is usually the case. Okay, so when we connect a resistor or a light bulb or something to a battery, sometimes we get this relationship where if we, and this could just even be a wire, right? So just a wire, and we're measuring how much current is flowing through the wire. So some materials have this nice behavior where if we increase the voltage across the wire, right, or the potential difference across the wire, we get a corresponding increase in the current, I. And so when you get this relationship that's a linear relationship, this is called Ohm's law. I mean, or it's ohmic. So very important for when we study circuits, which we'll be going on doing that next time. Sometimes material doesn't behave this nicely where it's nice and linear, but you get this, change, right? So sometimes it responds a little more slowly, and then it would respond more quickly. So Ohm's law tells us that, basically spells out this linear relationship, right? So if I increase my voltage, I get an increase in current, and then the slope of this is 1 over the resistance of the wire. So if I just rearrange terms, then I can rewrite Ohm's law like this, right? That says that the current I get will scale with the resistance. Is inverse to the resistance. So, right, so if I have a low resistance wire, I get more current for the same potential. And again, we mentioned that resistance is measured in ohms, right? And that's the Greek capital omega is the symbol for that. Okay, and looking ahead a little bit, we'll be doing circuits in our next unit, right? So we just want to look at how we actually diagram those out. So the battery is drawn here, right? So those are 2 parallel lines. One end is longer. The long end, we just by convention, is the positive end, okay? And then we may have some kind of thing like a bulb in here, or resistor. Resistors would look like this. Bulbs, sometimes you just see like this, and there's a little spiral wire through there. Okay, and so normally, thanks to Ben Franklin, actually, we draw current as the direction of positive charge flow, right? So we would always draw our current coming out of the positive side of the battery and going back in, even though in reality, it's the negative charges that are moving. So this is called conventional current. Okay, so that's I, and it's the, again, this is the flow of positive charge. Okay, which we just talked about that. And again, just note that the electrons are moving in the opposite way of what the current is that we're talking about. So when we refer to regular I, right, that is conventional current. And it would, and again, that's mostly what you're going to be dealing with. But then, you may, if it is talking about electron current, it would have to say that specifically, that it's electron current. Okay, and then finally, we're just going to finish up with Kirchhoff's law. We'll look at this again for circuits, but this is just one part of Kirchhoff's laws deals with how charge is flowing through the wire. And so the first part just says, if we're just looking at one continuous wire and we have a current over here, it's got to be the same charge moving up there and the same charge current flowing through there. And really, what that's talking about, charge passing through some cross-sectional area, right? So the statement just says that we can't have charge building up and piling up in places, right? If we have 5 electrons moving through that cross section, there's got to be 5 moving through that one at the same time. Okay, and then similarly, if you have a junction, so that when we start doing circuits, we're going to have wires that split, and so we can have some current here. Let's say that's I1, and maybe I2 through that branch, and I3 through that one. Okay, and so Kirchhoff's law says that whatever is flowing into the branch, I1, has got to be equal to what is flowing out, so I2 plus I3. And you can look at that in reverse, right? So if we had I2 and I3 coming together, the sum of this plus this has to give you what's coming out if they're all flowing this way. Okay, and I think that just about finishes up chapter 27.